All right, class, welcome to Friday. We had some homework questions. Why did I do that here? So we have ourselves 25, 51, and 65 from the homework here. We'll do 25. 25 is graphing this by using a graphing utility, right? Is that the way you say it? Graphing utility. So if you can use a calculator, go ahead and use a calculator. You guys can also go to Desmos, which is, I mean, there's a lot of other calculators out there, but desmos.com is another way you can just graph them. They're kind of nice. They color it for you as well. So that's kind of neat there. So right there, as far as test is concerned, Monday I'll tell you guys if you need a calculator for the test or not. Are we good? No, I'll tell you what you need for the test. Yeah. End of chapter 3. And so we have 4 sections in this section. I'm going to get rid of the last one because it's just application. We'll do application along the way. Yeah, we'll try to make that happen. Thank you.
I said Friday test. Because there's like
no time. Yeah. Yeah. I'll try to see if I can make it Monday or Wednesdays. Yeah. Gotcha. Okay. Let's go with it here. Let me get out of this. Let me go to the graphing calculator first. And let's go with, oh, I got 2 of them. Okay. Just need 1 of them. There it is. All right, let's go with it. Y equals over here. And I'm going to punch in 3 to the power of, and then what you have to do is you have to put a parenthesis in here because you're going to put in the x minus 2 inside a little set of parentheses here. So variable is up here. That's x minus 2. Close that off. That would be your parenthesis space. Then it's plus 1.
You have to put in parentheses.
Yep. Interesting. You have, let's see, some calculators, what they'll do is once you push into, once I do Desmos, you'll see it. Some calculators, what they do is they know if you're in the exponent, then you click the forward button on the arrows, and then it jumps back into your regular position here.
Parentheses are just letting the calculator know what's in the exponent and what's not.
Yeah, It's holding the exponent inside its own little space. Okay, so we go to, I usually go to window right here because the window, and I'm sorry, zoom, and I usually want to go to zoom standard number 6. So clicking on 6. And there it is, okay. Talk to me, those are doing it. Dylan, are we good now?
Yeah.
Sweet. Okay, yep, that's what I figured as well here. No problem. All right, let me jump to this right here. Come on. How many have used Desmos before? A little bit here. Show of hands. 1, 2. Okay. Let's see. So they have some math tools here. Click on that, and the graphing calculator shows up first. Dun, da, da, da. And then let's punch it in. Okay, it's gonna be 3. Again, to the exponent, it's actually your 6 key. Shift 6 on your on your keyboard, right? X minus. Notice it's staying. Ooh, that's interesting. X, right there. X minus X. My minus is not going through. Interesting.
Maybe if you include the parentheses before doing the number, when you use the exponent.
We'll do that here. X minus 2. Yeah. So it does need the parenthesis. And then you have to click the arrow to get back out of it here. Boom. And then notice what happens with the graph here. We're going to plus 1 to it here. And all it's going to do is just going to shift it up 1 unit here. So horizontal asymptote, what do you guys say? Yeah, y equals 1. Yeah, but the horizontal asymptote is only to the left. It's a one-sided horizontal asymptote. Okay, we're jamming. Are we okay with 25 now? Abe, are you okay with 25 as well?
Oh,
Okay, jump to 61 or 51, sorry. What does 51 say? Oh yeah, okay. 51 now. E to the x squared minus 3 is equal to e to the 2x. And this is using the property of 1 to 1. Can you solve the equations here? So with this one here, all we were interested in making sure our bases are exactly the same. Once our bases are exactly the same, we can just work with the exponents only. So it just becomes x squared minus 3 is equal to 2x. Because if the bases are the same and you take it to the same power, you're going to get the same number. So it's just a matter of what number do you need for that power. Notice I have an x squared over here, then I have an x. So once you see the little square right here, then you also see a variable somewhere else, you know you're going to have to factor or quadratic formula. So bring it over. Boom. And at that point, it's either factoring or quadratic formula, one of the two. So I have myself, let's see, two numbers multiplied to negative 3 at the negative 2. Perfect, I'll go with that. And then we're going to split them off each direction. Boom. Boom. And I have myself x equals 3, x equals negative 1. So I have two answers that work for this particular case. And real quick here, you guys, is that the answers in the back of the book? Yeah, okay. So once you solve it, you're done. You've solved. You good? Cool. All right. Boom, boom, boom. 51 good now. Boom. And 65. 65. So much better. All right. Ooh, a computer virus. Da-da-da-da-da. Infects the number V of computers infected by a computer virus increases according to this model right here. So it's 100 E. Hey, there's your E again. Remember how I said it? E is such an interesting base. It works in nature. It works with money. It works with population growth. It's just a fun base that just, it's interesting. It just occurs so naturally in our world whenever we try to model stuff. Okay, 5, 2, and T, where T is the time in hours where a computer virus is infecting a lot of computers. Okay, so let's see, in 1 hour, times 1. So again, having you use your calculator, you can also, I'm going to get out of here, use calculator, then let's see if I can use,
So it's 100 to 4.60 what?
4.6052. So 100, and then the E buttons are over here by the ln. So second function, boom, it already gets the caret in and already set us up your parenthesis. So it's 4.6052 times 1, which is really just going to be the same number anyways. Are we good? And who asked? Dylan, do you have the answers to that one or no?
I didn't want to help on it.
Gotcha. Okay. So within the hour, we have about 10,000 computers infected with this wonderful thing. Probably not realistic numbers though, right?
No.
We have to adjust, we technically have to adjust this little 4.60. It's too fast. Okay, we're gonna go with B. And then this one, 1.5, so kind of careful here. This is 4.0652 times 1.5. How do we punch it in the calculator? Is, real quick here, tricks of the trade, you guys ready? See how it says entry over here? What you can do is you can second and click it and it's gonna give you the previous entry that you had. If you want the answer, you click on the answer button. So this one needs a little bit of work here. This is gonna be this times 1.5. Notice by me multiplying it, but still keep it inside the parenthesis, I get to have all that. In there, I don't have to rewrite everything. Whoa.
2004.
Yeah. Let me check here. It seems it's slow growth after that. 4 computers in a half an hour.
Well, no, it was 2002 and 100,000.
Uh-huh. Let me just go real quick through here. Chapter 3:1. Three 165. Okay. I'll go with that. It was a spike initially, and it's kind of going slowly after that.
Oh, isn't that like a 1,000% increase, but it goes from 10,000 to 100,000?
Correct, initially in the first hour. So for some reason,
Well, you go from, well, in the first hour, it's, what is it, 10,000? And then you get to 100,000 full. So that's still a huge increase.
thousand. Right there. We good? Oh, got you. Okay, hold on. One. That was 10,000. Now we're at 100,000, right? Okay, gotcha. Yes. Okay, makes sense. Thank you. I thought it was only an increase of 4 units, but no, it's okay. And a 2 inside there. Again, same thing here on your calculator here. Go to it. Entry again. And I'm going to go over here. I'm going to plug in 2. And I got to erase all this. I'm going to go to delete on the rest of it here. Are we at 1 million now or no?
Yeah.
1,059,000.
1.0000636.
Oh, okay. Let's go for it. That's cool. So I get this answer. Isabel got an answer of 1.00000. 6. 1, 2, 3, 4. Then it has an e to the 6th. Okay, that's cool. So your calculator automatically converted to scientific notation. So, so we have to go 1, 2, 3, 4, 5, 6 units back, and then what we do, fill in the rest with zeros. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 4 zeros. You got a 6 here, and the rest of it you have to fill in with zeros. So it's doing an approximation. The number here is then 1,000,060. So if you don't get the exact answers at the back of the textbook, if it's an approximation, and you're still close, you're still good. Okay, are we good there, you guys? All right, let me jump to this one right here. So with Desmos, actually, let me get out of it. I'm going to go with, let's see, scientific calculator. Let me check that out. Love it. Okay, how about this? 1, 0, 0, 100. Do you have an E anywhere here or no? Wow. Oh, there it is. There's my little E right here. E to the, and back. So you got main, you got variables, or ABC keyboard, or you have different functions. So back over here, 4.6052. Click enter, and voila. Are we good? Those of you that want to just or need a quick little calculator here for that. I like that. That's cool. I haven't seen that in Desmos earlier. Has it been there? Anybody know? Has the scientific calculator been there for quite a while?
That's what I was using my phone when I keep track of it, like scientific calendar and everything, but.
Mm-hmm. Abe, is there a Desmos app? Is that the one you used or no? Okay, just use the phone. Gotcha. Okay, are we good there? You can jam now. Homework questions from 6.1 answered. Are we good to go on now? 3.1, thank you. Thank you for keeping me honest here. Okay, let's jam. This one, you got to put your thinking caps on. If you want to put 3.2, we're going to do something called a logarithmic function. It's cool. It's awesome. And we're going to try to
Our
unconfuse you.
brains might die.
Okay.
If you don't have a brain, you're not in danger. So you're safe. Chill.
All right, let's see. So what we have to think about is this right here. This definition of a logarithmic function is kind of unusual, or you can say that it's funky, okay? So we got to think about some stuff first. So don't write this down, kind of think with me. Just write down 2.1 logarithmic functions and their graphs. That's all you need to write down. The rest of it, put your thinking caps on. Let's jam. So we have, this is all about opposites, opposite operations. We're good? So we're going to take a look at a few things here, and then we'll define the log function. Okay, first things first, I'm going to define something that's adding. So y is equal to 2, or y is equal to x plus 2. Talk to me, that is an addition function, is that right? What do we, if we want to take the, oh, let's go over here real quick here. We've got to make a table, maybe not that far away here. So if you go x and y like this, right? Let's make 1, 2, let's put in 3 values here. I'm going to put a value in for 0. Answer, everybody, is 2. I'm going to put a, if I put a 1 into there, the answer is, thank you. And if I put in a 4 into here, the answer is awesome. So what we want to do here, wrong class, back to like 6th grade or something like that. If we want to do the opposite, real quick here, ready? If we want to go to the opposite of addition, what we do is we go like this. It kind of looks funny at first. Or we change it around. X is equal to y minus 2. Notice it's the opposite of addition. Notice also that your x's and y's on your table just got switched. So notice what happens here. If I plug in a 2 for the y, it gets me 0. Plug in a 3, 1, a 6 gets me the 4. Are we good? So we're doing the opposite of our operation, which switches my x and y to go backwards. We're doing a backwards way here. Okay, so let's do this here. Opposite of multiplication. And boom, that's cool. Like this, x and y here. We'll do 3 of them. And I'm just going to quickly go 0, 1, 4. Easy enough. Hey, that's easy. 0 is still equal to 0, huh? Boom. That's a 3. That's a 12. To go the opposite way, we got ourselves, see if this makes sense. Are we good there? That's the opposite way. Let's do one more, taking powers, because it kind of gets it. Because those two we understand easily, but taking powers gets a little bit more complicated. If I have like this, y is equal to x to the 2nd power. X and y. Let's see, 0 is going to be there. 1, let's keep it the same here. Everybody okay with, let's say 0, 1, and 16? Okay, now notice on this one's going to be kind of weird. Look at this. We were able to do an addition, right? Or we were able to do subtraction. We did one thing to one side, one thing to the other, right? Here we divided both sides by 3. Here, we can still do the same thing. It's kind of funny, but we add, well, we make a special symbol, right? It's a funky little symbol. Looks like this. That's my symbol, right? We put in a symbol and we say to ourselves, oh, the answer is x is equal to square root of y, right? So we use a symbol in order to get to the other side. And we say, hey, that's going to undo this. Are we good? Now, thinking caps on, let's go. Y equals a to the x. That's our exponential function, is that right? Oh. Anybody see a problem?
Can't take a square root because it's x.
Yes, this symbol does not work anymore because you don't take squares because the variable is actually in the exponent. What do we do? Okay, you guys ready? We make a symbol. And the symbol's kind of funny. It was invented by a French mathematician. His name was Nipier. And he said, we're going to change this up. And it's profound because really, at this point, math is stuck. Math is stuck because we have no way to sort of go to the other side. He says, I'm going to just make this little symbol. The symbol is going to be LOG. And we're going to put a little A in here. A is going to be it's all the subscript. And then we're going to put a Y on this side, and we're going to call this X. So let's see how this works. So Y is equal to 2. Let's go 2 to the X power. We know we've done that before. So 0, 1, 2. 0 in here gets us any number to the 0 power is 1. 2 to the 1 power is 2. And 2 to 4. Okay. So now let's switch it around. So it's going to be log base 2, we call it a base 2 of Y is equal to X. Whoa, okay, so let's go with the meaning here, ready? So 1 has to somehow go to 0, 2 goes to a 1, and 4 goes to 2. Let's see what the meaning is, ready? Question is, log base 2 of 1 means this. What exponent do you put on 2 to give you a 1?
0.
A 0. So 1 goes to 0. It's going to take a little bit to get used to. That's fine. So I'm going to go to the next one here. Log base 2 of 1 is equal to what? Or, I'm sorry, 2. Sorry, I was in. That's the 2 I need. Whoa, that did not sound good. What exponent do you put on 2 to give you a 2?
1.
A 1. So 2 goes to 1. Eventually. So one more. Log base 2, it gets a little easier here though. Log base 2 of 4 is, what exponent do you put on 2 to give you a 4? 2, hey, it's getting easier. Hold on, let's do another one. Log, forget this for now. Log base 2 of 16. What exponent do you put on 2 to give you 16? 4, because 2 times 2 times 2, or we can go a little bit smaller here. What base do you put on 2 to give you an 8? 3. What base do you put on 2 to give you a 32? 5. Log base, oh, I'm going to change the base on you guys here real quick. Log base 3 of 9. Hey, this is so cool. Okay, we're good there. Does that make sense?
Why is log though? That makes no sense.
Yeah, why can't it be like, have you never seen a log or like a squiggle?
It's a log.
This is the.
Logs
So-
don't have much to do with math.
So why did the French mathematician Nipier use?
Much.
Is that even a French word, logarithm? Is a log just interchangeable with a, with like the, Greek symbol?
No, there's no Greek symbol.
So, but it still results in the same thing?
Sure, I mean, you have different notations, right? So you could be at different fields, you could have different notation for log, but in mathematics, we use LOG. Now, why did he use logs? That'd be a fun presentation at the end of the semester. Like, why did Nipier use logs? Dylan?
I'm planning on doing something that's gonna hurt your brains.
Oh,
This
ouch.
might hurt your brains. Who knows?
Dylan, question?
What is the act of going from like y equals AX to log? Like, what are we doing in going from one to the other?
Sure. So it's just a process of mathematics. So remember how we started off with saying for polynomial functions, we had that right there, right? Oh, sorry. I'm using the screen here. Hold on. Let me get to a white screen here. Screen. white screen. Remember, Dylan's asking, why do we go from the other? It's just mathematical endeavor. You know, why did we do this? We went from here, and asked ourselves, hey, why can't we just switch the variable and the constant around? And all of a sudden that changed it into an exponential function. And then the next question always is, can I go the opposite way? Yeah, that's the next question. And then what does a graph look like? That's usually the kind of the processes that we see.
So it's an entirely new concept then, like you can't some of the things that we've known before.
Does it have application? Absolutely, it does have application, as we'll see in a little bit. Logarithms are actually the way we measure sound. Decibel scales are actually a logarithm.
So like you can't explain it by saying like you square root of y out and then it's not represented by log. Log is its own thing.
Sure, yeah. And the reason why Nupe had to do it real quickly here is because he had to build tables. So we call this really, well, let's go back through it. Okay. Nupe, he starts writing a book, and his book is 300, 400 pages, and all it is just values of this stuff. So let's take a look at it here. He does this. 3, he has 3 on one side, he has 1 on the other, and he has a column. So the question really is this: what exponent do you put on 3 to give you a 1? 0. So he really is not using the symbol LOG yet. He's just looking at this here. So then we go over here. 3, 3. What exponent do you put on 3? 3 to give you 3? 1. And we have a gap. What's my gap over here? 2 is the gap. So now the question is this: what's this? What? Okay, so that's 0, that's 1. And so what Nupe does is he goes back, and there's something called, in Greeks knew it, and kind of like doing long division, what they were able to do is they were used to be able to do exponential division. That's the way to do it. It's a long process. So he finds out that this is, you guys, we have to find out what that is. Can't do it right now. But he finds this number. And then what he does, he makes the table. 4, 5, 6, 7, 8, 9. And he knows this is easy. That's 2, right? And he starts making this table of values. And that's what Nupe's book is all about. It's 300 pages of just what's the exponent on the base that makes that number. And then remember, this is just base 3, right? He did base 2, he does base 3, then he goes on to base 4, base 5, base 6, base 7, and it's roughly a 300-page book. And it becomes like the standard manual for exponents.
Are we gonna get to find out what exponent?
Yes, we're gonna do it the easy way though.
Okay. Is that the part where you just tell us?
You click on a calculator called log. So why is the log button invented? It's so easy, right? And in fact, do you guys remember something called the mathematical slides? Anybody talk to you about slides?
No.
No.
Never heard.
Okay, I have to bring that in then. The way we used to do them in the past, before calculators, we had a slide rule. Slide rule would take the exponential number, you slide it like this, and you find out the base that you want. You got to work in the base. So base 3, you slide that over, you get your 27. You're like, oh, that's 3. Or you slide it to the 9, that's 2. And if you slide it to 6, it gives you the decimal number that gives you that. So all engineers, before calculators were invented, everybody walked around with slide rules, because that's what gave you those exponential numbers based upon which.
What if it was too big that they just have like one foot went across the room? What would they do?
No, it was probably about as big as a ruler.
Yeah, but what happens like if you have because obviously you can't fit all the numbers.
All the numbers, yeah.
What happens if you're doing it, you just have to guess and hope?
No, that'll be interesting. I have to
Oh
find
gosh,
out.
engineers guessing is never a good
That's
thing.
a bad place.
What were those things called, like ancient Greek calculus, like these slide maps for?
That was called rudimentary.
No. And it wasn't the Greeks either. It was, come on.
Egyptians.
The Babylonians?
No. Didn't go that far. We, I'm thinking about it. I can't think about it either. Guys, real quick, anybody know what is that, where you have the beads there? And
An abacus?
abacus, there you
Oh,
go.
that's what it is.
Yeah.
The Romans.
Okay, are we good there? Dylan, are we good now? So let's go back to where we are. I think it's pretty easy once you sort of see it though, right? So we've done this before. We did these right here. That was pretty easy, wasn't it? At least for some. Oh, we got one more to go. 525, log of base 5 of 25 is? 2. We good? Okay. So let's,
Five squared, not 5.
yeah, 5 to the 5th power, that's big. Okay, let's jam. Let's do the first 2, 3 examples, see how far we get. So what we want to do is just kind of get to the point of just changing forms one to the other. We good? Just real quick here, write it down if you need to. Now we can start writing down. So example 1. If you want to write it down, we'll go for it. Example 1.
Is that log 3?
It's log base 3 of 81 is equal to 4. That's true. That's a true statement.
Are we just writing?
But we want to write it from one form to the other. That's what we're doing. So I'm going to write the equation on top. It's log base a of y is equal to x. And that translates into, going both ways, of y is equal to a to the x. So we have to be able to sort of work from one form to the other and backwards and forwards. So notice where your a's are. A becomes your base on your exponent. The y becomes what's equal to, and the x, which was it equal to, becomes the exponent itself. Are we good? Sure. The a is the base. So the subscript for the log becomes your base in your exponential equation. The y value that's inside the log now becomes what is the value. So what's the value of the equation itself? And x, which was the value, now becomes the exponent. All right, another way to see it, my trig teacher taught me here. It's like a small little hook when you write it. You go from here to here to here. So a, take the x and equal to y. So base is 3. X is 4. X is 4 equal to 81. Is that true? 3 to the 4th power. 3 times 3 times 3 times 3 is 81. Boom, we're good there. Okay, can you guys do the next one if you have not done it yet? Sure. Log base 8. So again, we're just converting the forms, right? This one we'll actually get to know. So look at this, log base 8 of 4 would be 2/3. That's okay, we'll get to know there. But we're just switching forms now. So my base is 8, exponent is 2/3, and value is 4. Done. We're good?
Wait, so we don't need to like, we don't even know how we can write into that.
Yeah, we're just converting forms, one to the other.
Wait,
So this is called the logarithmic form. This is called the exponential form.
does any number to the 2/3 get you half of that number, or is that just a fluke here?
Any number. So let's talk about it here.
Does 16 to the 2/3 get you 8?
No.
Okay. I'm sure.
Good job, Owen. Good job thinking about it. The reason why is
60 to the 2/3 is 6 point something or other. Wrong.
what competition here
It'd be
happening.
nice if it did work.
Yeah. Exercise 2. Let's go. We'll finish off with this one here. Can you write the exponential form in logarithmic form? So can you write that equation going backwards here?
Sorry, can you wait a minute again?
Yep, sure. Yeah, please look at that. Sometimes the symbols, oh, you know what? That's why. I finally figured it out. Couldn't figure it out in trig class today. It goes into like pin mode for some reason. And so it doesn't have my little zoom in button. Let's see if this will work. Yes. Oh yeah, now it's cool.
Wait.
Cool, all right, and if you need to write it over again, that's fine. So this is log base A of y is equal to x, converts into y is equal to a to the x. Perfect, log. This is the, I think, the easier one. You just say, what's my base? What's the value? What's the exponent? Good there. What's my base? My value? And my exponent. Boom, done. Let's see, I think we have time for the next one. Let's do one more example just to sort of get it. And I took these exactly by the homework, so you guys can at least start your homework, because I didn't want you guys waiting and waiting to start the homework here. So once we finish this section, I'll tell you how much you guys can do of the homework. Should be pretty easy, right? And I want to follow it right away. All right, we've got 2.5 minutes left. So one more problem, go exercise 3. See, it does that. Okay, if I use my evaluate the function at the indicated value. And this is going to be pretty easy. You'll see this. This is what we were doing earlier. It says without using a calculator though. So we have to do it by hand. So we have a function now. Function is log base 16 of x.
16 to what exponent?
Yeah, let's bring in the.
To what exponent gives us 4?
16. What exponent do you put on 16 to give you a 4? Oh, not so fun. So in our minds, we're thinking this right here, right?
Oh, it's so mean.
Oh,
Is it a 2.5?
it's a 1/2. Abe is correct. Abe, why do you think it's a 1/2? Because it's a good guess.
It was a valid guess. Because
Uh-huh.
I thought 4 squared is 16.
That's exactly
16 is the
why.
opposite.
Absolutely, yes, So in math, if we say this guy is going to be, 4 squared. Good there? Now those are the same. Hey, that's what we dealt with the exponents there. 16 is actually 4 to the 2nd power. I'm going to use an x right over here just because it's variables. These guys are gone, so I'm solving for this. 1/2. Are we good there? So real quick in our minds, we should think of this. A half in the exponent really just means square root, right? Because isn't square root of 16 4?
Oh, yeah.
So this guy's just 1/2. Okay, 2 more problems. Let's go. And we got 20 seconds. So 10 in there. Oh, notice this guy does not have a base. There's no base here.
Is that just log 1 then?
Ooh, interestingly enough, if there's no base, the base is, not that 10.
Not that 10.
Base is 10. 10 is the default for base of logs. And we'll see why next time here. So what exponent do you put on 10 to give you a 10?
1.
1. Okay. Ooh, and the fun part. B to the -3. Okay, log base B of B to the -3. What exponent do you put on B to give you B to the -3?
-3.
-3. Of course, because that would make sense. Okay, we'll stop there. You guys able to do questions on the homework? Write this down if you need to. We're able to go up to 37 on the homework.
37, don't forget that. What did you take?
Oh no, hold on, sorry. That was just for Owen. We're able to go to 29.
Wait, why do I go to 37?
Oh, because you left, but no, it's up to 29.
Thank you. Have a good weekend.
Thank you so much. You guys have a good weekend. All right, did we learn something new today?
I don't know how to do this.